points that, sorry. So yeah, Jack mentioned a lot of good points, but I compiled some slides here to show some of the content, talk a bit about the class. So first, I was just going to introduce a bit about the CCC. I know Jack already did a bit of this, but just some points from my perspective. So as you probably know, it's an annual programming contest for high school students. It's 5 problems ranging in increasing level of difficulty. And just one thing I would add about the problems is that generally the first 2 questions, as you saw, the certificate of distinction cutoff is around 30 most years, which each question is worth 15 points. So generally the first 2 questions are close to good enough for their certificate, but from this class, I'll be teaching a lot of algorithms, data structures, and higher level problem solving skills that will help you reach those later problems. But generally speaking, the first 2 are on the easier side, and then question 3, 4, 5 is when it really requires the preparation and stronger knowledge of algorithms and problem solving. So as Jack also mentioned, top performers are invited to the CCO competition each year. And the strong CCC score is not only good because you did well in the contest, but it can also help you get into one of the University of Waterloo's competitive math, computer science, or engineering programs. So in terms of the class overview, what you can expect to get out of the class is learn the relevant topics in terms of algorithms, data structures, problem solving that are targeted for CCC senior preparation. Also explore a wide variety of different competitive programming topics that are useful for the CCC senior, but also will help you in preparation for other programming contests like the ECOO and other online contests, if that's something that you're interested in, which I would definitely recommend to become interested in that, as it's really good practice for the CCC. So the course is going to focus on both algorithm knowledge, so things like data structures, other forms of algorithms that you will need for many of the more challenging problems that you'll find on the CCC senior contest. But also at the same time, it's going to really work on your problem solving skills that is especially needed for the harder CCC problems. So algorithm knowledge alone isn't good enough to solve some problems. It requires strong problem solving skills. And that's something that comes from practicing a lot of different forms of problems. So I'll also give you practice material and problems, both from past CCC competitions and other contests that you can use to practice the algorithms that I teach, as well as work on problem solving and just get as much practice as you can. And at the end of the class, what you can expect to get out of it is not only be very, very solid for those earlier problems on the CCC senior competition, like the S1 and S2 questions, and be able to do those in a short time frame during the contest, but you can also expect to have the tools and knowledge and practice to be able to seriously attempt and get points on and solve those later S3, S4, S5 questions, which are the ones that will really distinguish you for getting the honor roll, and even in some cases, if you perform extremely well, qualifying for the CCO. So as you saw from those problem averages that Jack showed, the averages on those questions are pretty much 0 most years. So it's really going to be a big advantage to have a lot of the tools and practice to be ready for those problems. So some of the topics, a sample of some of the topics that will be taught in the class. Some of the main areas include basic to advanced data structures, dynamic programming, graph theory algorithms, and I added in ad hoc, which is pretty much questions that don't necessarily fall under one of these main categories of algorithms, but they're just as important because it's problems like the ad hoc problems. You're going to be able to come up with solutions. You're going to have to come up with solutions on your own that don't necessarily correspond to an algorithm. And those types of problems appear very commonly on the CCC. And while learning all these algorithms, you'll not only be learning them, learning where they can be applicable, learning the theories behind them, how to use them, but also by practicing these algorithm related problems, you'll simultaneously become a better problem solver and get better skills. So you're better prepared to approach more difficult problems. So, and then the final thing I'm going to talk about before getting into an actual lesson on a topic for today is my teaching strategy for this class. So my plan for the class is during each class session, I'll break it up into one or multiple specific algorithm topics. Note that they will be more specific than the ones shown on this slide. They will be specific data structure, specific types of dynamic programming problems, or specific graph algorithms. And then, sorry. Yeah, from this point, I'll break the class up into one or multiple of these topics, which for each topic, I'll introduce the topic from a more theoretical perspective so that you can understand where it can be used, why it's efficient, and things, and how to implement the algorithm. And then I'll show an example of the algorithm in real problems so you can see how the algorithm is used and how you can implement it into different problems. And then I'll also provide additional problems for you to practice independently. And these will be on the DMOJ online judge. I'm not sure if you've heard of it, but it has thousands of problems and it contains all of the past CCC questions and many other questions that are good for practicing your problem solving and algorithm skills and having access to past contest problems. And then at the start of each class, I'll take up the problems that I give for you to work on independently, and you can ask questions about them and I'll go through the solutions. And finally, throughout all of the classes, feel free to please ask any questions you have. I will answer them. And also if there's any adaptations in the material or topics that you'd like to see, or if there's a specific topic or problem you want to go over that I didn't necessarily introduce myself, then I'm happy to do that. Okay, so does anyone have any questions about that? Please let me know if you do. All right, so everyone's good. Okay, so now that I've gone over some of the class, I'm going to teach a lesson on something that's a pretty important and fundamental topic in competitive programming problems and contests, and that's maps. So one thing I'd like to note before starting this is that I'm going to be doing all the teaching in C++, and I would recommend that you also do the problems and do the contests in C++. And the reason for this is that languages, like as Jack showed, the three languages that are allowed for the CCO are Java, C, and C++. So that shows that these are the main ones, but between those, C++ is by far the most popular. And the reason for this is that it's more efficient than many of the other languages. So even on the CCC page, Waterloo, on the University of Waterloo CCC page, they say that the CCC senior and contest will not actually be solvable in all languages, but it is guaranteed that all the problems are solvable in C++. And in addition to this, C++ has many built-in functions and operators that can be used to help you solve all the CCC problems and many other problems. Okay, so in terms of maps, I'll introduce it here. So when I start this lesson on maps, it's going to be somewhat assume that you have a bit of foundational knowledge, maybe in C++, maybe in another language. But if you have any, if you don't, that's okay too. If you have any questions about any of the syntax or anything of regarding the fundamentals, that's fine. I can go back to that and explain that. So actually, before I start on maps, I'm going to talk about something that's very important in competitive programming, and I'm going to be referencing quite a lot in this lesson and in other lesson, and this is time complexities of your code. So I'm not sure if you've heard of this before, but time complexities, pretty much what they are is it's for any algorithm or code you write to solve a problem, you're going to have to analyze what the time complexity of the code is. And essentially what the time complexity is, it's a measure of how efficiently the code runs. So it's represented in what's called big O notation, which is written like this, an O with, and then you put the time complexity in the brackets. So some of the main time complexities you'll see are O of 1, O of n, O of n squared, O of n log n. And what these mean is the time complexity represented in big O notation is essentially going to be a representation of how many operations or how long your code is going to take to run with respect to the input. So when I reference n here, n is going to likely be, it's going to be a variable given in the input. And the reason I chose n, it can be another variable, but most problems do use n for the question. So you're going to take the variables they give you in the question and think about your algorithm, what it's going to look like. And then you're going to say how many iterations or operations is your code going to run to solve the problem in terms of the input size. So I'll give some examples here. So let's take an O of n question. So let's say you were given a problem and you're given in the input an array of numbers and you wanted to find the maximum value in the array. The time complexity of this problem, or the best solution to this problem, would be O of n. And the reason for that is to figure out what the largest element in the array is, you're going to have to loop through all the elements of the array and keep a maximum of which one is the largest element so far. And that, when you're looping through each element in the array, that's going to take n operations. So if the input is n, then the time complexity is going to be O of n, because you're doing roughly n operations with respect to the input. But if you had a question where you read in the input an array of n numbers, but for whatever reason your algorithm required you to have a nested loop through the array, so you have a loop for each element, and then for each element you're going to loop through every other element again in a nested loop, that would be n squared, because for each element in the array you're going to be doing n more loops, which is O of n squared. So the reason these are important is because for any problem you're doing, you're trying to minimize this time complexity. So O of n is better than O of n squared because it's less operations, just like O of 1 is better than O of n. So O of 1 would mean that there's no connection between the input size and how long your code takes to run. So if you're just reading in one number and then you're outputting something, say you were outputting double the number, that'd be a very simple example. That would be O of 1 because it's really just like one operation. So you're always trying to minimize your time complexity. And the reason is every problem you'll do on whether it's an online judge or especially in contests, it's going to have a time limit for how long your code can take to run before it stops running your code and you don't receive any points on the problem. So, for example, you want your code to run under this time limit, and the best way to do that is to minimize the time complexity of your code. So O of n will always run faster than O of n squared here, because if n was 10 to the power of 6 in the question, O of n would take approximately 10 to the power of 6 operations to run and output the answer. But if it's n squared, then it's going to take approximately 10 to the power of 12 operations, which that's going to be way too slow. And as a general rule of thumb, when you're doing these problems, when you think of your time complexity, which I'll show more examples later, but when you think of your time complexity, you want to plug in the variables in your big O notation, and you want to get that answer. And if that number exceeds approximately 10 to the power of 8, then your code will likely TLE. It will exceed the time limit. That's what it's called on the online judge, TLE. So, and you don't want your code to exceed the time limit, because then you don't receive any points on the problem. So I hope that makes sense. It will make sense more with more examples as I show. So now that I've given a bit of an introduction into time complexities, I'm going to introduce the topic of maps. So in C++, maps are a data structure that I would say is it's a data structure that I use quite commonly in many competitive programming contests and problems, not only because it makes certain problems easier to implement, like it makes the code actually easier to write, but also they're strong in terms of their time complexity, meaning that it would take, using the map data structure will make for a more efficient code than other methods that don't involve a map. So what a map is, essentially, it's a list of pairs of data types. So each pair in the map will contain a key and a value. So if you think of a map as a list of any two data types, so in this example here, it's a map of characters and integers, but you could also put a string here, a double here, an integer in both places. It doesn't matter. You can pick that. It just means that this map here is going to be storing a list of pairs of characters and integers. And what you can do with this list is have the integer here correspond to the character here. And when you want to access the corresponding integer at a certain character, you access it like this. So m, and then in square brackets of the character a equals 1. You're assigning the integer for the character a in the map to be 1. Or you can increment it by doing this plus plus. That just means to increment the value by 1. So then it would become 2 here. So this might remind you of an array. If you're not familiar with arrays, they're essentially similar to a map as I described, except rather than this data type you put as the key of the map, it's always going to be being of your choosing. For an array, it's always going to be an integer, right? So if you have an array of length 100, then there's going to be 100 memory locations that you can access in. So let's say we had an array here of length 100, then you can access any of these 100 locations by doing array of 0, array of 1, anything like that. So that's how you'd access the value at that memory location. But with an array, the drawbacks are, for one, you can only have an integer as the key. Two, you have to set the size of the array at the start. So whether it's 100, 1,000, a variable amount, you're going to need to allocate all of those memory locations right from the start. And arrays tend, for a competitive programming question, a contest question, you can only usually make an array up to a size of about 1 million to 10 million, in that range, until you're going to get some kind of error, namely a memory exceeding the memory limit, which is similar to exceeding the time limit. If your code allocates too much memory by making an array too big, you're not going to get the points on the problem. So that can be an issue. Whereas with a map, nothing is allocated in the map until you actually allocate it yourself. So when this map here called M was initialized, there's no memory so far has been allocated in the map until here we access the map at location, or for the key A, and it assigns a 1 to it. So now that value of A is a key in the map. So that's only one location of memory so far. So if you have a list of key characters or numbers that you want to store in a map, it's only going to store them if you need to store them. Whereas with an array, if you set the array to 1 million, all of those locations are allocated before you even use any of them. You may very well not need to use many of those locations. So the good thing about a map is each time you access the map like this or like this, it's only the time complexity of this is only going to be O of log n, which is good. Log n grows very slowly, and it's generally very similar to O of 1. So for an example, when you have an array here, let's say of just size 100, for example, and you say integer x equals array of 1, even though we haven't put anything in the array, to access this location in the array, that's going to be an O of 1 time complexity. That's essentially just one operation to access that. It doesn't matter how big your array is or anything. That's one operation, and that's very good. Now, maps are a bit slower. They are O of log n, but that's still very close to O of 1. So what that means, and in the big O notation for the time complexity, what n means is the number of keys in the map. So for example, the map starts with 0 keys, but then when you put the A into the map, that's going to be 1 key. So that's going to be like n. So if you have 1 million elements in your map, 1 million keys of the map, then each time you access a key in the map like this, it's going to take log of n. So if that case, it would be log of 1 million, which is still very, very small compared to what it could be. So the reason log n is very good for a map is because the alternative to that is storing a list of these pairs of data. So you would, instead of putting the A into the map, you'd be storing a big list of pairs of character and integer. And every time you wanted to access one of them, you would have to loop through that whole list to find it, which is extremely slow. That the time complexity of that is O of n, which is not good, because if you do that many times, then that will be way too many operations. So that will TLE in most cases, time limit exceeded. So as I also said, it's good for memory because it only assigns the memory once you put the key into the map here. So I hope this makes sense so far. If you have any questions, feel free to just speak out and let me know if anything doesn't make sense so far. If you want me to go through anything again, please just turn on your mic and let me know. But yeah, if there's no questions so far, so now that you know how to, this is how you're initializing the map. I'll get rid of this. This is how you're accessing elements in the map. So what this is doing, it's setting the key, the location with the key A here, because that's the character as the key. It's setting it to 1. And then here it's going to increment it. And then you could set another location, that's the character B here. Let's set it to 5, let's say. And then you're storing all this data that for problems when you use this will be important, and it will be important to access that and change it, all of which is done in these efficient O of log n operations, which is very useful and for many different applications. So now let's say you have in your map some different keys, you have some different data types you're storing in your map. Now let's say you wanted to loop through all of the keys in the map. So there's a very simple way you can do this in C++. And by the way, if you're not familiar with C++ very much right now, and say you know Python as an example, a map is very similar to a Python dictionary. If there's anyone who knows Python well, but in C++ not as much, it's similar to that and has the same functions pretty much. So here for iterating through the map, this is how you're going to iterate through a map in C++. And iterating through the map is just going through all the memory locations in the map. So when you would iterate here, you'd be going through the memory location with key A and the one with key B, because those are the only two that have been set in the map here. Like, note that when you do something to the key A, you're not actually putting in a new memory location in the map. It's the same one. You're just updating the corresponding value at that location. But when you put in B here, that's a new key in the map. So here, this would go through A and B in the map. And you'll notice here, it says auto. So I here is just the name of the variable that's going to show up in the loop for each key of the map. So through each iteration of the loop here, you're going to have this variable I, and the variable type of I is going to be a pair. I don't know if you've heard of a pair before, but they're also useful for many problems. So if you think of like an integer as a variable type, a pair is similar. It's a data type, but rather than it just being one integer, say, it's going to be two values that correspond to each other. So in this case, this map is going to contain a bunch of pairs of characters and integers just like this, that can be expressed as a variable of their own each. So for example, when you set B here, this is going to be a pair where the first location is B and the second one is 5. So each time you loop through, you're going to have this value I, that's the current memory location in the map, which is going to be a pair. So the map is sorted based on the key. So A would come before B here. And when you have I each time, it's going to be, as I said, a pair. And to access the first element of the pair, so the character, you're going to do I dot first. To access the integer, the second location, it's going to be I dot second. And then so here I've just assigned the variable key to I dot first, just to show that you can extract the character that is the key in the current location of the map, and you can access the value, which is I dot second. So for this, this is just useful because if you want to go through everything in the map, you can do it with this iteration. Now here, I'm going to show how this runs right here. These are commented. This is the map. And I'll just get rid of this. So I'll run this. Hopefully, I haven't. So here, what you can do is we have our key and our value. Now, let's say we want to output this to the console. we can just do C out our key, followed by a space, followed by the value. And this is going to, and then this is just to end the line. So this is how we're going to output everything. Let's hope this. Yeah. See, so what this does is this should make sense since we have our A and our 2, which we put in the A here, set it to 1, and then incremented it by 1. So increasing its value by 1. That's why we have A2. And then the B we just set to 5. So this is going to be B and 5. And then, so yeah, this is just showing the elements of the map. As you see, it did it in alphabetical order. And yeah, so that's pretty much the basics of maps. Does anyone have any questions? Just feel free to turn on your mic and ask about maps. And then I'm going to show an example of a problem where you'd use a map. No questions? Yeah, feel free to ask.
Excuse me.
Yeah, go ahead.
Can you show the first line of code? You have some code about the stdio things.
Yeah.
What does it mean?
Oh, that's a good question. So this is pretty much just a line of code that I put and that I would recommend you put at the top of your main function here. And all it does is it makes inputting and outputting faster, more efficient. So for many problems, you're going to be inputting a lot of data, and that inputting takes time in your program to run. So if you put these at the top of your code, it's going to make that more efficient. So then it's going to take less time to input it out and output, which in some cases, actually for some questions, this line of code here is the difference between getting a time limit exceeded and passing the problem, just because some problems have a lot of data and it takes time to input that data. So this just speeds up the inputting and outputting. Does that make sense?
Yes. Does that mean there's no buffer reading and output?
Wait, sorry, could you repeat that, please?
Okay. So that means you make the buffer zero size.
I think, yeah, that sounds correct. I'm not entirely sure of the logic behind it, but I know this is just something that a lot of people that's recommended for these problems. What you said is probably right about the buffer, and it makes it just faster to input and output.
Okay,
yeah.
Thank you.
All right, no problem. Okay, so if there's no other questions, does anyone else have a question about anything or maps or whatever? Okay, so if we're good on that, then I'm going to show a problem that is a problem that what's interesting about the problem I'm going to show is it's a problem that you cannot solve without a map, or at least I don't know of I don't think I've seen a solution that doesn't use a map for it, because it essentially just uses what maps are made to do. So can everybody see the screen here? I have the problem pulled up. If you have a DMOJ account, you want to pull it up yourself, you can do that as well. I'll read through the problem, but if you want to read it, follow along, then you can go ahead and do that if you'd like. So what this problem is, it says Andy is traveling through the galaxy. His mission is to categorize the planets that he passes. So there are K types of planets. He passes by N different planets, and each of these planets can be classified as one of these K types. So you help Andy on his mission, blah, blah, blah. Whenever he passes a planet, he will tell the assistant the type of the planet, and this assistant must tell him how many previous planets there are of this type. At the end of his journey, the assistant must also report the total different types of planets that he has passed by. So, if you haven't seen a problem like this, the way it formats it is it gives the problem statement at the top explaining what the question's asking essentially. Then it gives your input specification, which this is what your program's going to have to read in the input. So the first line is going to be n and k as mentioned in the problem. So n, number of planets that he passes by, and k is the number of different types of that those planets can be. So the next n lines will each have the type of planet that the ith planet is. So it's going to give a list of n numbers. Each one is going to be, and then it gives your constraints. Each one is going to be between 1 and k, because it's going to be one of the k types of planets. And here it also gives the constraints on n and k, which n is 10 to the power of 5. That's pretty good. That's suggesting right away, that's suggesting an O of n or O of n log n solution, most likely. Because if you have O of n squared with 10 to the power of 5, that would be 10 to the power of 10, which, as I said, if it exceeds 10 to the power of 8 approximately, that's probably going to be too slow for the problem. So right now we're thinking probably O of n or O of n log n. And then k, this is also an important constraint. K can go all the way up to 1 billion. And then it gives, sometimes problems give subtasks. So like you can earn partial points for certain constraints where they'll make the problem easier for that part of the grading of your solution. But right for now, we're just going to go for the whole solution given these constraints, these ones here. So then it's going to give you some sample, it gives a sample. Sorry, something just happened on, can everyone hear me okay? All right. So here it's going to give you n, which is 5, and then it's going to give you k, which is the number of different types of planets. So then we get our list of n numbers. We go 1, 4, 4, 3, 4. And then this is the sample output. So this is what the correct output is going to be for the problem. So like the question asked, when you get your first input, you need to output how many times a planet of that type has already occurred. Well, since this is the first planet that you're inputting, obviously it's going to be 0 since no other planets have come before it. So it's going to be 0. Then you get a planet of type 4, which is also 0 because there's no 4. Then you get another planet of type 4, but you're outputting 1 here because there's already been one of type 4. So you need to know that. And then here you get one of type 3, hasn't occurred yet. So we're outputting 0. And then you get another one of type 4, which there have been 2 already. So that means you're outputting 2. And then at the end, it wants you to output the number of different planets that have occurred so far, which is 3 different types because we had 1, 4, and 3. So I hope that makes sense. That's just understanding the problem so far. I'm going to open this up and I will try go along here and I'll go through a solution that won't work first so you can see why it won't work for one, and then I'll show the correct solution that actually uses maps. So the first thing we have n and k. We're initializing the variables. Then we input our variables here. And then we're going to get a list of the planet types. Now we could input this into an array or something, but for now we can just do a loop that goes from iterates n times, so 0 to less than n. So that's 0 to n minus 1, which is n times. And then we'll make a variable called planet. We'll input that. Now, let's say one solution might be to store these in a list. So I like to use, this is another thing that I want to mention. I know like arrays are the most common way of storing lists, but personally, I find that vectors are easier to use for cases like this, because with arrays, sometimes you need to initialize it like globally. So out here for it to not produce some issue in the code. Whereas vectors, you can just initialize right here. And also with vectors, you can add elements to the end of the vector, as well as initializing its size when you initialize the vector. So I find them easier. They're fairly simple. I'll show you how this works. So this is the syntax for initializing the vector. So this is saying we have a vector of type integer and we're calling it planets. And that's all you need to do for now. And then when we want to add our new item to the end of the vector, we can just do planets dot push back planet, which is our new value. So that's, you can use an array also, but vectors do allow you to do this pushback function. So, which can help, as well as if you want to set the size, say to n, you can do that. Or if you wanted to set it to size 100, something like that, you can also do that. So for now, we don't want to set its size at all because we're going to be using the pushback function to add them as we go. So now we're receiving our input, and for each one of these, we want to know how many of that type have occurred before it already. So one way you could do this, well, you could say, well, all of the planets that have occurred so far are in the vector because we're putting them in each time at the end of this loop when we input it. So what's the most intuitive way to see how many there are? Well, we could loop through the whole vector. I'm going to make another loop with j variable this time. And then we can keep a counter how many there are. And the vector has the function dot size, just so you know how many to loop to here. Oh, that's a mistake. J plus. These should be j. Then here we'll make a variable called count, let's say, and we're going to start it at 0. And we'll say, well, if the current one we're looking at, which is we're going through the vector of planets, which it's the same way of accessing memory locations as an array. You use the square brackets along with the index. If it equals our current planet, then we're going to increment the counter because that's going to add to our answer that we want to output. And then here we can output our answer. Oh, whoops, we called it count. And then this would work for the first type, for the first part of the question, and this would output it. And then at the end, we need to find how many different types of planets we've seen so far. Well, we can have a variable called different out here. And each time we input a planet that hasn't occurred yet, we're going to increment this difference. So what would be if the newest planet is a different one, a different type that hasn't occurred yet in the input, we're going to be our count will be 0 because when we search through all the planets, it will not be, there won't be any of that type. So then we could just say if count equals 0, then we can do difference, increment it using ++. And then here we're just going to output difference at the end. So this, as long as I haven't made any errors in the code, would output the correct answer, which is good. But when we do our time complexity analysis here, we have a loop that goes to n, and then inside it, we have a loop that goes to approximately n. Like it's going to be 1, then 2, or it's going to be 0, then 1, then 2, then 3, then 4. And like this is a math thing, but the formula for like the sum of the first n numbers is going to be n times n plus 1 divided by 2, right? So you don't really need, when you're doing the time complexity analysis, I'll just put that up here. When you're doing that, you don't really worry about n times n plus 1 divided by 2. You don't worry about constant factors. And a constant factor is if you have, say, a divide by 2 or something like that. We want to keep it as simple as possible, and we're just going to call it n squared. This algorithm is n squared because we have a loop that goes all the way n times, and then this one goes worst case n times. It's going 1, then 2. So that's going to be approximately n squared, which if we go back to the problem, n goes up to 10 to the power of 5. So that's 10 to the power of 10. This is going to exceed the time limit for sure. So now we need a better solution. Oh, sorry, I'm on the wrong one. We need a better solution than n squared to solve the problem. So what we can think of here is each time we input a planet, what we're trying to figure out is how many of that type have occurred already in the input without looping through all of them, which one way of doing this is doing something. Essentially what you're going to do here is you're going to use memory to save time in the code. It's kind of about the memory time trade-off here. So rather than looping through everything that's occurred and checking, because that's too slow, we could possibly think of an array. And an array, each index would store how many planets of that type have occurred. So every time, say you got a planet of type 1, you're going to do, like, say we initialize the array, we would do array of 1 plus plus. I haven't made the array, but you do something like that. And then to get your answer here, you could just do cout array of planet, which would give you how many have occurred so far, assuming you'd actually put this here at the bottom of the loop because we don't want to include the current planet. But that sounds good. The time complexity of that would be O of n, because it's n loops here, and each one within the loop, this accessing the array, that's just O of 1 time complexity. So that would be good enough, but we have an issue with that. How big does our array need to be? Well, it needs to store potentially it needs to have indexes that potentially go up to however big k is, because we could have a planet of type k, and k goes up to 1 billion, and that's way too big for an array. Like I said earlier, a general rule of thumb, you really don't want to exceed 1 million to 10 million for an array, because you'll likely get a memory error or some kind of other error. So this is where the maps solution comes in, because we can store a key with a value, but we only allocate the memory locations that we need. So if we can actually get rid of our vector now, because we're not going to be looping through that at all. And we're going to get rid of this loop, and we'll be inputting our planets here. But up here, what we can do is make a map. And in this case, it would actually just be a map of integers and integers, and I'll call it frequency here, because the integer, the key, is going to be the type of planet. The value is going to be how many times it has occurred. So each time we input a planet, we can do frequency of planet plus plus at the bottom of our loop once we output our answer. And our answer for how many times has the planet occurred so far is going to be frequency of planet, because planet is the key, and it's going to, the value is going to be how many times it's been incremented here, which is how many times it has occurred so far. Now for the second part of the problem, we could have this difference variable, and we could check if it's 0, if this value is 0, increment it because it means it's a new type. Or there is a simpler way because of a function you can do with a map, and all you need to do is frequency, which is our map, dot size. And that's going to tell you how many keys there are in the map. And how many keys there are, that's how many different planets there are, because each different planet is going to be a key in the map. So you can see here, the map not only gave it the correct time complexity, and the time complexity here, if you want to think about it for a sec, it's going to be not n squared, we loop n times. It's not O of n, because keep in mind, every time we access into a map, it's going to be a log n operation. So the time complexity now is actually n log n, because we have a loop n times, and then each time we do this or this, it's going to be log n operations, because we're going to have approximately n elements, worst case, in the map, and it takes log n time to access it. N log n, if you want to plug that into your calculator to check for n equals 10 to the power of 5, is going to be well below 10 to the power of 8, which, as I said, was the approximate limit. So it would be, yeah, it'd be 500,000, because log would be 5. So that's well below 10 to the power of 8. It's going to pass. And also it made the code simpler to write, which I said earlier that sometimes maps help make the code simpler to write. This is definitely one of those cases. And it also made the solution be fast enough to pass. So this is a good example of a map problem where the map data structure can be quite useful. So that's one example. Now I can give you what I normally do at the end of each lesson. I'll give a problem or two that you can try that incorporates the data structure. So there's a problem on a past CCC problem here, it's called Rajaman.CCC 2016 S1. Now for this problem, you don't need a map, but the map is very helpful for writing the code. So, and also there's a bit of a problem solving element to the problem. So that's a problem that if you want to give it a try by yourself after that, go ahead, and then you can work on maps and just have a problem to practice. And yeah, that's also, if you want another problem to practice, this one isn't for maps, but it would be to work on pairs. If you want to try it, it's CCC 2020 S1, and that one is a pair problem, and you're also going to need to do some sorting in that, which the sorting part, it's literally just out here. I can show you that right now. We're almost finished here, but if you have an array, let's say, call it a just array of whatever length we set it as, or actually I'm going to say here, let's say you have a vector. You can sort the vector like this, and that sorts all the elements of the vector, which the time complexity of this sorting is O of n log n being the number of elements in the array. So that's that's the most efficient sorting algorithm there is. And it does it for you. It's just a built-in C++ function. So yeah, you can try that one, CCC 2020 S1, and also try Rajaman CCC 2016 S1 if you want 2 problems to try. So yeah, that's the lesson for today. I hope you guys enjoyed it. I'll stop sharing my screen. Do you have any questions? First of all, yeah, does anyone have any questions about the problems or maps or anything like that?
Can you show us how to output a map ordered by the key?
Yes, I will go back to and I just need to share. You can see now where So this is outputting the map in the order of its keys. So here, like I said, you have, this is like a loop. It's going to iterate through all the elements of the map. I is going to just be the current element in your loop that you're at. And then I is going to be of type pair. The first dot first is going to be the character, which we initialized here, but it could be any type, it could be integer, whatever. But in this case, it's a character first, and then the value is second. So here we're just storing them in variables, but then let's say you wanted to output them. You just can output key and you can output value here. And then that will just give you a list of all the pairs with their key and their value. And it's going to be sorted by the key. So if it's a character, it'll be alphabetical. If it's numbers, it will just be sorted, increasing. Does that make sense?
How about if I want to order by the value?
If you wanted to order by the value, then you can do that, but it would be there would be an extra step to outputting it in order by the value, since a map is stored in order of keys. But what you could do is you iterate through the map in order of key here, and then what you can do is you could make like an array or a vector. I'll just make here, make it of a pair of, you can reverse the key and value. This is a bit complicated, but, and then we'll just call it our map or something. And then each time here, you can add to the vector the pair, but you want to put the integer first, the value here, the value first and the key second. And then this will, and by the way, this is just how you add values of a pair. You put these curly brackets, you put the value in the first element in the first spot, the second here. So here we want our value first, then our key. And then what you could do is you could sort the vector in the same way that I showed earlier, and then you could just loop through that. And then you'd have it in order of value, and you'd have your corresponding key with it in the pair. If that's, or what you could do is you could just reverse the, actually you might not want to do that, but this is one way you could do that. That makes sense?
Yes. Can I just create a new map and I put the value as key and the key as value?
You
then
could do
output
that.
it?
You could do that also. That would be the same time complexity and everything as doing it with a vector. But yes, you could create a new map and just reverse them too. Yeah. All right. Are there any other questions from anyone? Okay. So yeah, I think that's.
Sorry, just
Yeah.
one more question. How to get the recording of this this meeting?
I think
This
Jack
record
or
is
Glenn.
this record is only be provided to the student, the former student.
So once we registered, we should get the recording, right?
Yeah, please note you have to be the grade 9 to grade 12 student, and you have to show your student ID, and you so and you can get it. Yeah.
Okay. Well, okay, sure. We'll send the tuition and hopefully get the ID.
All right. Okay. Does anyone else have any other questions about what I explained or anything about the class?
Okay.
All right.
Anyone have any questions? Okay. If you have questions, please don't hesitate to ask Ross.
Yeah.
If you don't have, so the class will be ended. Yeah, today's class is only 1 hour. Thank you, Ross. Thank you for giving so amazing class. Thank you so much.
Yeah, absolutely. Thanks.
Thank
Thanks
you.
everyone for coming.
Bye.
Ross, you complete from this session. So I will handle the customer. Thank
Okay.
you.
All right. Sounds good.
呃
Okay.
Thank you。其他的顾客有什么问题吗？如果关于这个班呢有什么问题吗？我可以回答你们的问题。您有什么问题吗，李先生？
没有，谢谢。
好的，您如果想参加班级的话，就像我前面说的一样，就是 e-transfer 那个 tuition 到这个我们这个 accounting，I put in the chat window。
对这个课多贵来着？
这个课，现在的价格是现在是869，现在价格是869。这个课1个礼拜上3次，在8月份那个之内结束，每次是2个小时，是2.2个小时，所以一共是26个小时。
是每星期上3天？
对，每星期上3天，对。
哪天？几点？
我们现在初步的计划是这个，每天是11点到1点钟。如果您这个付过费以后，您如果对这个时间有不同意见，您可以参加这个时间协商。如果协商不成的话，我们退款给您，全额退款。如果协商，一般来说的99%的情况下，我们都能够协商成功的，就是说一个比较合适的时间。
OK， 好，谢谢。
好的，
再见。